Okay, so let's get started. Now, today, I want to introduce a new cohomology theory called Cech cohomology. And that will give us another way to compute the Rham cohomology. What is special about Cech cohomology is that it depends only on combinatorics. It doesn't depend on geometry or topology, It depends only on how the open sets of a good cover intersect. And in order to prove that theorem, okay, I'm going to first prove a theorem I stated last time. So last time we introduced the Cech-de-Rham complex, and that is just the complex of differential Q forms on p-1 fold intersections of an open cover. Okay? And it's a double complex because it depends on two indices, P and Q. And then we can augment this complex by a -1 column. And this column is the kernel of the first difference map. Okay? So here in the 0th column, you have Q forms on open sets, and the difference map takes it to Q forms on intersections. So the kernel of the difference map means that these Q forms on open sets agree on intersections. Therefore, they give you global forms on M. So the new column, this augmented column, consists of just global forms on M, okay? And so this column has cohomology, just the Rham cohomology. Okay? And you have this restriction map going into the double complex. And the theorem is that, this restriction map induces an isomorphism. Okay? Okay. Because the double complex can be made into a single complex with differential D. D is just the sum of the vertical differential with the horizontal differential, okay? But you need to put a sign, right, on the vertical differential to make the two differentials anti-commute, okay? So this gives you a way to calculate the Rham cohomology using the double complex. And we proved last time that all the rows are exact because they are just the generalized Mayer-Vittorus sequences. Okay? Yeah, okay, so let's prove this generalized Mayer-Vittorus principle, that the restriction map gives us an isomorphism from the Rham cohomology to the cohomology of the double complex, okay? All right, so I'm gonna put that down there. So I begin with a lemma. It's called the shortening lemma. And okay, and what it says is that if you have a situation like what we have here, where the rows are exact except possibly at the 0th term, and you have a cocycle in the double complex, say of, degree n. Now, if it's a cocycle, that means big D of this is 0. Okay, so this has to go to 0, and then now let's write the horizontal one. Usually we write it as D prime, but I'm going to write it as delta. Okay, the vertical one is D double prime, and the horizontal one, I'll write it as delta. So if you have a cocycle, then, okay, big D has to be 0. So that means delta of this has to be equal to minus D double prime of this, okay? You have something like this. And then at the end, delta of this has to be 0, right? If you have a cocycle. So the hypothesis is that the rows of a double complex K are exact except possibly at the 0th term. Okay, that's the situation we have here, right? I mean, without this augmented column, the rows are exact except possibly at the 0th term. Then a cocycle C, okay, of degree n can be shortened in its cohomology class so that it has only the top component. So what the lemma says is that if you start with a picture like this, okay, then you can find an exact cocycle, exact cycle, sorry, an exact chain, so that when you subtract the exact chain from C, you'll get this. You end up with a cocycle with only one component, and the component is in degree n, okay? So listen, yeah, here I have a picture of degree 2. It can be shortened in its cohomology class so that it has only the top component. Okay? So if you start with a cocycle, an arbitrary cocycle of degree n, you can move it in its cohomology class so that it becomes this. Okay? That's the lemma. Okay? And okay, how do we prove this? So because you start with a cocycle, DC is 0, okay? Now DC is the, say, let's just do it for degree 2. And now, so this D is D double prime plus delta, right? So for each term, you get two terms plus d double prime C1 plus delta C1 plus d double prime C2 plus delta C2, okay? And you see these terms, they all have bi degrees. That just means that they are in different boxes. So this one is going to be here by itself. But these two have the same bi degree, right? Delta C0 is in the same box as d double prime C1. Okay? So these two are in the same box. These two are in the same box. This is in a different box. This is in a different box. Now the whole thing has to be zero because it's a co-cycle. So that means each box has to be zero. Okay? So each component of the same bi degree has to be zero. Okay? And so, yeah, so delta of C0 has to be zero. But the rows are exact. What can you say about this C2? It goes to zero horizontally. And the rows are exact. Yeah, so that means there is a element here in this box that maps to B2, okay? And so let me call that element B2. Okay. So B2 maps to D2. And now I'm just gonna, if I subtract big D of B2, I will get rid of this C2, right? So, okay, so let me write that down. So since the rows are exact, delta C2 equal to 0 implies that there exists a B2, so it's in the previous box. In the preceding horizontal box, such that delta B2 equals C2. Okay? Okay, and now you look at C minus DB2. Okay? So this is going to be, well, you'll have, you'll have a lot of stuff. I mean, let me see. Oh, yeah. So what would that be? Let me. So it would be this whole thing. The double prime. No, just a minute. It would be C0 plus C1 plus C2 minus dB2 is D double prime B2 plus delta B2, right? And but delta B2 is C2, so this cancels that. And so you get C0 plus C1 minus D double prime B2. And you see C0 is here, C1 is here, and then D double prime B2 is here too. So you are only in two boxes. Okay? So this is in the same cohomology class as C, but it's shorter. Yeah. Okay. So let's see. Yes, I think I should keep this theorem. So let's see. All right, so I guess maybe I need to erase this part. Okay, so in this way, C minus dB2 is in the same homology class as C, but shorter. So it's a cocycle that is shorter. Okay? You can apply this again to shorten it again. So apply the same procedure to shorten it. So you can keep on doing this until you end up with just this term. But at this point, you see, because the row is not necessarily exact here, so you cannot continue the procedure, the shortening procedure. Okay, so we can repeat until we end up with CA0 in the top, K0 n. And because the row is not necessarily exact, at this point, you cannot continue. Not necessarily exact at the 0th term. And you can't continue. So the process stops here. Okay? Yeah. Okay, so what this means is that, yeah, so we get like a co-chain B such that C minus dB is equal to A0, and it is in just one box, okay? So that's the lemma. Every cocycle can be shortened in its cohomology class so that it ends up in just the top box. All right? Yeah. Okay. And so now we can prove the theorem. Okay? So we want to prove the theorem. And to prove that it's an isomorphism, right, you just have to show that it's surjective and injective. Mhm. Okay, so let's start with surjectivity. Let me see, how far up does it go? No, I think it's still better this way. Okay. All right. So surjectivity of the restriction map. Okay. Or uh-huh. Um, okay, so you start with the cocycle. Let C be a cocycle in the double complex by the shortening lemma. You can assume that it has only that top component. Okay? Okay, so you have A0 there, and you want to show that it comes from something. Okay? Now, it's a cocycle, so what you know is that D double prime is 0 and delta A0 is 0. Okay, so since D of A0 is D double prime A0 plus delta A0 is 0, and these two terms are in different boxes, so both of them has to be 0. So D double prime of A0 is 0, and delta A0 is 0. Mhm. Okay. But if you augment the double complex, then the rows become exact. So, like each row is just a Mayabi-Torah sequence. So since the augmented rows are exact, so there exists an omega in omega n. I usually let n be the dimension of the manifold. So maybe I should call this k, okay? I have a k cocycle. So there exists an omega, which is a k form on M, such that R of omega is A0. Okay, so I have an omega here. Uh-huh. And then, we have a commutative diagram. d omega, and this is R. Okay, so by the commutativity of the diagram, this omega, it goes to d omega and it goes to 0. But what do you know about this map R? The restriction map. I mean, it's a restriction of a form to, the open sets of the open cover. What do you know about this map? Remember, the augmented rows are exact. This row is just the generalized Maya-Vittora sequence, and it's exact. So the map R is injective, right? Yeah. So d omega goes to 0, R is injective, that means d omega is 0. So that says that it's a closed form. And so that omega defines the cohomology class. Okay? Yeah. So like if you look at the picture, then it's kind of obvious, but you can also write it down. When you write it down, it becomes less obvious. So yeah, so by commutativity of the diagram, okay? So R of d omega is d R omega is d A0 is, no, this is the double prime is 0. And then since R is injective, the omega is 0. Okay? Yeah. So, so omega defines the cohomology class, and this cohomology class maps to the cohomology class of A0, which is the same as the cohomology class of the original cocycle C. Okay? And this proves surjectivity. All right, yeah. Now let's prove the injectivity of this restriction map. Okay. Let's see. So now I assume that I have a cohomology class on M that maps to 0. In cohomology, right? So I assume that I have an omega here, and then R maps it to R omega, and that R omega is exact. So suppose omega is a closed form on M, and R omega is equal to D of some cochain. And okay, and this cochain, okay, is C0, C1, C2. maybe it's got more components, but let's just do it for 3 components. And so now if you write this out, now you see that this is d double prime C0 plus d prime delta C0 plus d double prime C1 plus delta C1 plus d double prime C2 plus delta C2. Okay, and now let's group together the things that are in the same box. Okay? This is in the same box. These two are in the same box. So you see, that means what? That means R omega has to be d double prime C0. And these two, they have to add up to 0 because there's nothing else on the left-hand side. So, yeah, let me just write it like that. This has to be R omega, and this has to be 0. This has to be 0, and this has to be 0. Okay? Yeah, so you've got this picture. This goes to 0. But the rows are exact. So by the same argument as before, you can get rid of this C2. Okay? By the same argument as in the shortening lemma, okay, now I don't have a cycle, right? This C is not a cycle. But this part looks the same as before. Okay? Yeah, so by the same argument, as the shortening lemma, we can shorten this C. We can shorten C in its cohomology class until it has only the top component. A0. Okay. So this is the picture now. You have omega and it goes to R omega, and then C has been shortened to A0. Okay. And this is the picture. So i.e., there exists B such that C minus dB equals A0. And A0 is in K of 0, K minus 1, right? This is degree K, this is degree K minus 1. And then let me see. So, so, right. So R omega is dA0, and that's d double prime A0 plus delta A0. Yeah, if you just look at the picture, you see that d of A0 has to be R omega. So that means delta of A0 has to be 0, right? So this, yeah, so this part is just this part. This is R omega. And so this part has to be 0. Okay? Yeah, it's clear from the picture. And then you know that the augmented rows are exact. Okay, so since augmented rows are exact, so there exists a tau that maps to this. Since delta A0 is 0, there exists a tau in omega k minus 1 of m such that R of tau equals A0. Okay, and then now let's see. So look at the commutativity of the diagram. Yeah. So D, just a minute. I want to show that D tau is equal to omega. Okay, so let's look at D tau. Now, what do I know? Yeah, so D tau, if you apply R to it, by the commutativity of the diagram, it's D double prime R tau. Okay, but the restriction, yeah, commutes with D double prime. Just a minute. R D tau. Oh, okay. So the commutativity of the diagram says that this is D double prime R tau. Okay, by commutativity. And R tau, oh yes, R tau is A0. And D double prime of A0, yeah, D double prime of A0 is R omega. Yeah, so that's because R tau equal A0, and then yeah, R omega equals dA0, which implies that D double prime of A0 is R omega. Okay? And then since R is injective, this says that R tau, D tau is equal to omega. Okay? So so we started with an omega, okay, that maps to an exact element. And now we show that omega is exact. Okay? So what we have proven is that That's, we started with omega, so that R omega, the cohomology class of R omega is 0. So this is R star of omega. And that implies we have found that omega is D of something, so its cohomology class is 0. That's what we have shown. And so therefore, R star is injective. Okay. So this proves the generalized Mayavi-Torres principle that that the restriction map from the de Rham complex to the double complex induces a linear isomorphism in cohomology. So it means that you can compute de Rham cohomology using this double complex. Okay? It gives you a new way to compute de Rham cohomology, but it seems like the double complex is more complicated than the Rham complex, right? Yeah. So, okay, you don't usually compute the Rham cohomology this way. Although in theory, it gives you a new method. Okay? And yeah, so that's why now I want to introduce the Cech cohomology. Okay? Let's see. Yeah. So, you know, yeah. We look at this double complex, and we have augmented it by a column that is the kernel of the first difference map. Okay? But, you know, when you have a double complex, whatever you do to the columns, you can do to the rows, right? So we can also augment the double complex by a bottom row that is the kernel of the first D. Okay? Yeah. So let's do that. Okay, so you okay, so you're going to have a term here that is the kernel of the first D. So this D, this is D on functions, on open sets, right? What is the kernel of D? I mean, you have, so like, if I have an open set, say U, and I want to know what this kernel is, okay? So D from omega 0 of U to omega 1 of U has a kernel equals what? What's the kernel of D on functions? I mean, this is so basic that you are afraid that you might get the answer wrong. D is the exterior derivative. What kind of functions satisfy df equal to 0. Locally constant functions. So the kernel of D are the locally constant functions on U. Okay? And like this D here, it just means you are taking the exterior derivative of functions on each open set of the open cover. And so the current, so like if you have D going from 0 forms on all open sets, so the kernel of this D is it's going to be the direct product of locally constant functions on each open set. Okay, so I will use this notation where yeah, so the locally constant functions on U, I will write it as R bar of U, okay? Yeah. So then the kernel of the direct product, would be the direct product of like locally constant functions on each open set. Okay? And this I will call C0 of U, the open cover U, and then instead of forms, now I have R bar. R bar means locally constant functions, okay? So we can augment our double complex with this row, which is C0 of R bar, C1 of U R bar, and so on. And then this map, I mean, this is just a subset, right? The locally constant functions, they are functions. So this is just inclusion, okay? And the delta is the difference. So it will take the difference of locally constant functions is locally constant. Yeah, so we can augment the Cech-de-Rham complex with the bottom row. And this bottom row will satisfy, del square equal to 0. And you can define its cohomology. Okay? And that will be Cech cohomology. Okay, so we'll do this after the break. Let's take a break for 10 minutes. And then we'll continue with Cech cohomology. Okay, so let's write down what we just discussed. Okay, we can augment the Cech-de-Rham complex with a new bottom row that's the kernel of the first D. Okay, and yeah, so we can augment the Cech-de-Rham complex with a new bottom row. Let's see, that would be K of star -1, which is the kernel of V on let's see, on on C0, no, just a minute. So it would be C star U omega 0 to C star U omega 1. And it is the direct product of locally constant functions on U. Okay, I think I should put a P here. No, yeah, right, P. That's right, yeah. U alpha 0 to alpha P. Okay, and that's what we call CP of U R bar. Okay, so that is the new bottom row. The new bottom row. And this map is just inclusion. And then delta is the same delta. Huh? Okay, yeah. And so this this complex, so now you have C star U R bar with the alternating difference operator as the differential. Okay, so this is a differential complex. And therefore, you can take its cohomology, and that's called Cech cohomology. The Cech cohomology of an open cover. Okay, yeah. Maybe I'll write it here. Cech cohomology of an open cover. Okay. Yeah. Now, you notice that you're just looking at locally constant functions. So you don't need a manifold. You know, it makes sense on a topological space. This means you can define Cech cohomology for a topological space. Definition, let U be an open cover of a topological space. M, okay, and it should be indexed by a linearly ordered set. A. Then the Cech cohomology of the open cover, H bar of U R bar, you know, it's just the cohomology with the differential delta of this complex of locally constant functions on open sets. Okay? So that's the definition of Cech cohomology. Okay. And now we would like to generalize, you know, the Maya-Vitoris principle to Cech cohomology. Now, in the proof of the Maya-Vitoris principle, you know, that the Rham cohomology is isomorphic to the cohomology of the double complex, we needed the fact that the rows are exact, or the augmented rows are exact, okay? So now what we need is that the augmented columns are exact. Um, and the columns, they're just the Rham complex on each open set, right? What does exactness of a sequence mean in terms of cohomology? Exact means that the kernel is equal to image, right, of the preceding one. What does that mean in terms of cohomology? Yeah, it means the cohomology is zero, because cohomology is the kernel over the image. And exactness means the kernel is equal to the image. So exactness of a differential complex means exactly that the cohomology is zero, okay? So exactness of a column, it means exactly the same thing as that the homology of the column is zero, okay? And then in the augmented complex, the columns are just the de Rham complex on each open set, or intersections of open set. When do you know that the cohomology of all the open sets are zero? Like here, in order for this column to be exact, the cohomology of all the open sets have to be zero. And for this column to be exact, the cohomology of all the pairwise intersections have to be zero. For the next column to be exact, the cohomology of all the triple intersections have to be zero. What is the condition that can guarantee that? If you have a good cover, because if you have a good cover, then all the finite intersections are diffeomorphic to Rn. And so the cohomology, would be zero except in the zeroth term, right? Yeah. Right, yeah. But yeah. But if you add this extra term, the locally constant term, then it would all be zero. Okay, so yeah. Okay, so if you have a good cover, U is a good cover, then, okay, the cohomology of the columns is all zero except at the zeroth term. But if you augment it by introducing the locally constant functions, then, the columns will all be exact. So if U is a good cover, then the cohomology of all augmented columns are zero, because all the open sets are diffeomorphic to Rn. And so that means all the columns are exact. So the columns of the augmented, so the columns of the double complex augmented with the bottom row are exact. So all columns of double complex augmented with a new bottom row are exact. Right? Then we have exactly the same situation as the Maya-Vittoria sequence, except now we're talking about columns instead of rows. Well, then whatever we did before is true now, except we're now talking about columns. So this gives us a theorem. This theorem says that, so if all columns of the Cech-Rham complex, well, it's actually for any double complex, right? So all columns of first quadrant double complex augmented with a bottom row are exact, then the homology of the bottom row induced by inclusion is isomorphic to the homology of the double complex. Okay. And if you apply this to the Cech-Rham complex, it would say that Cech homology is of a good cover is isomorphic to the cohomology of the double complex. Okay, yeah. So now let's apply it to the Cech-Rham complex. Then you get this theorem. So apply to the Cech-Rham complex with a good cover. So we get the theorem. So if U is a good cover of M, then the Cech cohomology of the good cover is isomorphic to the cohomology of the Cech-Rham complex. But we already know, that for any manifold, the de Rham cohomology is isomorphic to the cohomology of the double complex. So this is isomorphic to the cohomology, the Rham cohomology of M. Okay, and so yeah, so this theorem says that if you have a good cover, then the Rham cohomology can be calculated from the Cech cohomology of the good cover. And this is easy to calculate because you only have to look at the open sets and how they intersect. And this theorem also shows that the Cech cohomology of a good cover are all isomorphic. That wasn't obvious from the definition, but since the Cech cohomology of a good cover is isomorphic to the Rham cohomology, and this doesn't depend on, there's no cover here. So a corollary is that the Cech cohomology of all the good covers are isomorphic. Okay? All right, so let's do an example just to show you that it's easy to calculate Cech cohomology. So let's do the Cech cohomology of a circle. Okay, I have a circle and I need a good cover. Now, so I choose an open set. Okay, that's like this arc. Well, if I had just another one, that wouldn't be a good cover because the intersection would have two components. So I actually need three open sets to get a good cover, right? So if I call this U0, U1, U2, that's a good cover. The intersection of any two is just an interval, which is diffeomorphic to R. Okay, so that's a good cover. And so let's write down C0. Now C0 would be the locally constant functions on the open set. So it's RU0, RU1, RU2. Okay? What are the locally constant functions on an interval? I'm just testing to see if you are awake. You just have to be awake to answer this. What are the locally constant functions on an interval? Yeah, just the constant functions, right? So this is RRR. Okay? And then C1, so C1 would be the locally constant functions on pairwise intersections. Two. Pairwise intersections are also intervals, so it's just RRR. Okay. And so let's call these constant A0, A1, A2. And then delta from C0 to C. So you have delta from C0 to C1. Okay. Yeah. And delta. And this is the complex, right? You have to calculate the cohomology of this. And let's use the same board. Okay. So delta is going to take A0, A1, A2 to three numbers. On this component, it's the difference of A1 minus A0. And then the next one would be A2 minus A0. And the last one is A2 minus A1. That's delta. And that means, okay, the kernel of delta would be when all the numbers are equal, which is R. And the image of delta would be, it would be R3 over the kernel, right? So R3 over the kernel of delta, and that is R3 over R, so that's R2. Okay? And so H1 of this open cover, H1, well, it's just the kernel of delta because the image is 0. So it's just the kernel of delta. So it is R. And, oh, sorry, that's H0. Yeah, H0 here is the kernel of delta. And H1 would be the kernel of the next delta, which is 0, so that's everything, R3 over the image of delta, and that's R3 over R2, and that's R, okay? And so what you get is that HK of the open cover is R for K equal to 0, 1, and then after that, there's nothing. So 0 for K greater than 1. Okay? And you see that this is the same as the de Rham cohomology of S1. Okay? So, yeah, so Cech cohomology gives you another way to calculate de Rham cohomology. Okay? Yes, and it's a very simple way. It only depends on how the open sets intersect. Okay, so we're going to stop here today.